In this video, we're going to look at the molecule that transfers oxygen in our blood, and that is hemoglobin. So hemoglobin is a tetrameric, that is, has 4 subunits, protein found in erythrocytes, which are basically red blood cells. So it has 4 sites for binding oxygen, and hemoglobin is why our blood appears blue or red. So when there's no oxygen in hemoglobin, it appears blue. When there's oxygen in hemoglobin, it appears red. And in erythrocytes, hemoglobin is the majority protein in those cells. In fact, 34% of the weight of erythrocytes is made up of hemoglobin. So we call this an alpha 2 beta 2 tetramer, which means it has 2 alpha subunits and 2 beta subunits. Now, this isn't alpha helix or beta sheet. Rather, we're saying the alpha subunits look alike and the beta subunits look alike. And what is interesting is that each subunit of hemoglobin looks a lot like myoglobin. You can fit the 2 over each other and they are very similar, which means that they share ancestor evolutionarily. Now, if we talk about symmetry, alpha and beta promers have a C2 symmetry and a pseudo D2 symmetry. And what's interesting is that talking about hemoglobin, oxygen binding to hemoglobin will affect the structure of our protein. So there's a big difference in structure between deoxy and oxyhemoglobin. And you can just see some of that to begin with. If you look at this hole in deoxyhemoglobin, it is much wider than the hole in oxyhemoglobin. So that's just one example of some of the structural differences. And we'll look at those more in depth in later videos. But there's a lot of communication between our different subunits. So at the alpha 1 beta 1 interface, that is between subunit alpha 1 and subunit beta 1, and conversely alpha 2 beta 2, there are 35 residues in contact. In alpha 1 beta 2, there are 19 residues in contact. So we have a lot of residues from different subunits that are interacting with each other. So it makes sense that we could shift the entire molecule, shift all 4 subunits at once. And a lot of these residues that are in contact are actually hydrophobic residues. And so that is why this protein can come together. It has a lot of hydrophobic residues, so the hydrophobic effect will push these residues together, and now you have a tetrameric protein. Now, if we look at the binding curve for hemoglobin, first let's look at myoglobin. It looked like this, hyperbola. Now, we can calculate what the binding curve for hemoglobin should look like, and it's this dotted line. We do that by using our dissociation constant like we did in the previous video. But what is interesting is that when you do measurements of binding experimentally, you have this sigmoidal curve. This sigmoidal curve is saying that hemoglobin is cooperative. And what cooperative means is that when hemoglobin binds one subunit, or one oxygen in one subunit, the affinities for oxygen in the other subunits are affected. Well, we know that hemoglobin has positive cooperativity. That is, when one subunit binds oxygen, the other 3 subunits want to bind oxygen more, or scientifically we would say it has a higher affinity for oxygen in these 3 subunits. And on this picture you can clearly see that each subunit has a heme, so each subunit can bind oxygen. All right. Now, like I said, hemoglobin is the protein that carries oxygen in our blood, and that's because the P50 for hemoglobin is 26 torr. So if we go to P50, it's right here. So that means that 50% of hemoglobins will not have oxygen at 26 torr, which is roughly the pressure of your veins. So in your veins, hemoglobin won't have oxygen, so they will be giving oxygen off to the cells. Unlike myoglobin, which even in your veins would never give away its oxygen. So it's much better for delivering oxygen throughout the body. Now, when we talk about cooperativity, we have a specialized plot to show that. But first, let's look at the equation. So hemoglobin plus NO2 goes to hemoglobin bound with oxygen N. So this N means number of oxygen molecules. And so our fractional saturation equals the pressure of our oxygen raised to the power of N, and divided by our P50, which is what pressure of oxygen where half of our hemoglobins are unbound, raised to the power of N, plus PO2 raised to the power of N. We call this N a Hill coefficient, and it tells us our degree of cooperativity. If N is equals to 1, that means we have positive cooperativity, or a ligand binding in one subunit increases the affinity for ligand binding in the other subunits. N less than 1 means you have negative cooperativity. So if oxygen were to bind to hemoglobin and N was less than 1, the other subunits would not want to bind oxygen. Affinity would go down. N equals 0 means no cooperativity. So if we look at the Hill plot, what you do is that you actually have the log of your fractional saturation. That's one way to describe this. And so if we look on our Hill plot, we have myoglobin right here has a slope of 1, right? So that means it has no cooperativity, and we are plotting that with this equation. So N log POT minus N log P50 for myoglobin. When we solve that equation and we can plot it like this, we get an N of 1. When we solve this equation for hemoglobin, we see something interesting. At low pressures of oxygen, hemoglobin looks like it has no cooperativity. At high pressures of oxygen, hemoglobin looks like it has no cooperativity, P of 1. However, during this change, we see that the slope of hemoglobin becomes 3. So we are saying we have positive cooperativity here. So what that kind of is saying is that without oxygen being bound, hemoglobin doesn't have cooperativity for oxygen, which makes sense because for cooperativity you need something to be bound to set off that chain reaction. At high pressures of oxygen, all of our subunits are bound, so we no longer see any cooperativity. While in between, we have maybe 1 or 2 ligands bound out of a possible 4, so we're seeing this positive cooperativity. We're seeing that we want to bind more oxygen now. And that's it for this video. I will see you in the next video.